So Chinthaka, now we have some idea about this RTD, how it can be mathematically represented with respect to temperature and so on. Yes. Do you see any problems or limitations?
So I was wondering, in the table, the thermocouple didn't require a power source.
Correct.
But then RTD and the thermistor, as well as the P injection integrated kind of silicon devices, required some current or voltage. So I believe in this case, what is this current that we are giving this kind of device?
So what you're saying is you have this resistance Rx that you want to measure.
Yes.
Which is R naught into 1 plus alpha T.
Mm-hmm.
I'm taking only first order.
Okay.
So how do you measure this?
Yeah, what kind of current do you get?
Yeah, so I can send some maybe non-current and then look at the voltage drop. Correct.
Like a voltmeter, just correct.
Yeah. I was reading, it says about 1 to 5 milliampere.
1 to 5 milliamp.
Yeah, okay. Not much. So I was thinking, why not 10 milliampere? You will get better voltage drop here. Or why not 20 milliampere?
But you're forgetting something, right?
What?
Because when you increase the current, you're also going to increase the heat.
Oh, okay.
And that might cause a problem.
So this Rx has got some resistance, of course. I forgot that. Yeah. So what you meant is there is I square Rx losses. And then there will be some heating.
Yes. And that could add to what we're trying to measure.
So then the Rx will change due to that.
I believe so.
It's possible.
Yeah.
Exactly. So that is called self-heating. Correct? I mean, you are trying to measure some temperature. For that, you have introduced an RTD. You are sending current through that.
Right.
There is some heating happening. Yes. It says, okay, now the temperature has increased.
When in reality, the environment temperature is the same.
Yes. But one way you cannot avoid it because you need to send some current.
Exactly. So, which was my next question. This 1 to 5 milliamperes, is that the current that you send so that it doesn't increase the temperature too much? Or is that how you decide on the current? So how does that?
Maybe I have a different way to bring in that. So, see, I have seen not RTD, just resistor in the lab. If you see, I mean, there is some color coding, etc. But they are usually small.
Mm-hmm.
But then, let's say this is 100 ohm resistor. I've seen 100 ohm resistor, much bigger size also. Again, 100 ohm. I mean, the drawing is not
I know what you're trying to say. Yes.
But same resistor value, but different sizes. What may be the reason?
Well, R is equal to rho L over A, right? So is it do with that?
That is not the reason. Let's say it's made of same material. So it's okay. That means it's not to do with this aspect, right? So this is also meant to, let's say, use in a circuit. There will be some current going, there will be I square R loss. So larger the size, you will be able to, or if you look at the transformers, etc., they have got large size due to the coil and other things. But then you can also maybe see
dissipate,
finished, etc., to the side.
And we need dissipate the heat better.
Dissipate the heat better. So this guy can, the larger one has better heat dissipation capacity. So this will be able to handle more current.
Okay. Even though the resistance
is the same. So in the similar way, the packaging of the RTD
will become larger.
Yeah, become larger, or the material used for packaging, etc., decides what is its, heat dissipation capacity.
Okay.
Or if there is a, temperature rise of, or if there is this much watt loss in that, how much temperature will increase? Okay. So I have a small calculation that way here. See, they have given an example. Let's say the thermal resistance is 50 degrees Celsius per watt. And RTD has got a temperature, a resistance of 250 ohm. Now, if you're sending 5 milliampere, the I square RTD is some watts. I mean, it will be not watts, milliwatts.
Yeah.
Right. 5 milliampere square into 250. So that much watts is generated. Yes. And what it says is this package is this way, that if there is 1 watt loss, there will be 50 degrees Celsius increase. So from this, we will come to know what will be the increase in temperature. So if you are using 5 milliampere, over time, you will have 0.31 degree Celsius increase. So this much output will be there due to self-heat. Right. So if you are measuring 100 degree, it will read as 100.3.
Now, how is this related to the error then?
Exactly. This will be seen as an error.
So this is the error.
This is the error.
Along with some other errors,
Yes.
I suppose.
Yes. This is one of the
contributors to
Yes, exactly. So now if you want to reduce this, I can maybe instead of 5 milliampere, I may choose to use 1 milliampere. It will be much less. Yes. So,
different types.
Yeah. So what I meant is, you asked the question, how much current we should send?
Yes.
It is to do with, to minimize or keep the error due to self-heating low as possible. Now, we have to look at the packaging and see if X amount of watts is generated, how much amount of change in resistance will be there.
So, but what then is the trade-off when it comes to the package? I mean, why can't you use, let's say, a package with better dissipation?
Yeah, I think it's cost.
It's cost. So it comes under cost here, which is the last row that you were talking about.
Yes, yes. Now, the self-heating is one of the problems. What else you think? What else problems, or what will be the other source of error?
I'm just looking at thinking about the finished product that you showed in the first slide. I mean, that also I saw some wires coming out of it, right? Some lids.
Correct. Yeah. The sensing element will be somewhere here. Then you have got,
right? Yes.
Yeah, wires up to there.
Right. So
even the measurement system may be a bit far. So the wires still continue.
Right.
That's correct. So this means
you're adding some resistance.
Exactly. So this means you have the, let's say, RX here and the measurement unit here. There is lengthy wire connecting these two. So there is some maybe RL1 and RL2, the lead wire resistors, or the resistance due to the lead wire. Right. Now, if you are measuring at these 2 points, we will be seeing RX plus RL1 plus RL2.
Yes.
Also, if these lead wires are exposed to temperature,
I was going to say
that will also change.
Right.
So this can actually introduce, large amount of errors if the lead wire resistor is exposed to temperature and it is also similar in range of value with respect to RX. Otherwise, it can be a big problem.
Yeah.
So what do we do?
Make it short.
Make it short, but that may not be possible. See,
that's true.
My measurements unit is here. Let's say this is some meters away, RX.
Then
avoidable, yes. So that is where people use, yeah. I see. See, there is a resistive element and then packaged like this. This is what we have discussed. It's just 2 wires coming out of it.
Correct.
But sometimes I see 3 wires. And sometimes 4 wires.
So are you taking the added resistive components as something separate?
I don't know from this, how is it possible to separate?
Some kind of reference, so you can get rid of that component.
I'm not sure. So maybe we can just discuss this 4-wire. It says most accurate. Then the 3-wire comes,
Probably become more obvious.
Yeah. So let's maybe discuss this briefly. So what we are saying is, you have got a RX to measure. And then my measurement unit is here. Whichever way I am measuring. Now, you have 4 wires coming out. 2 here and 2 here. How will I make use of this somehow to get rid of RD? I mean the RL1 and RL2.
Don't tell me there's some Wheatstone bridge arrangement here.
So maybe we can think like this. Let's say I have a current source. One of the approaches. Suppose if I have a current source, I give it to the outer ones. Okay. Of course, there will be RL here. There will be lead resistance for this. RL1, RL2. Yes. Cannot avoid. But since this is a current source, there will be same amount of current flowing through. Correct. Now, I need to measure the voltage across, this is the contact that you have made for the current to, let's say C1 and C2, current to enter and current to leave. Now, my meter is here. Let's say I am measuring this voltage, this side, the measurement side. So, there again, I am going to connect 2 wires to this terminal. And this terminal. Let's say this is P1 and P2. Okay. And this has got RL3 and RL4. So, this RLs represents the lead wire resistance. This region is my measurement node. So, what we said is, let's say this current I is flowing through this, and then it has got I into Rx voltage there. I measure using a voltmeter here. Yes. Of course, since it is current source, RL1 and RL2 will not have any effect because the same current has to flow. They are in series. Yes. How is this error due to RL3 and RL4 are the more? Sorry, how? See, this one, there will be current I flowing because RL1 and Rx is in series. Yes. Same current flows through this. Yes. So, effect of RL1 and RL2 will not be there.
Okay, yeah.
But RL3 and RL4, how is their effect removed?
Because now we are measuring the voltage, aren't we?
I'm measuring the voltage. So, yeah, you are right. Because this voltmeter or the system that I use here to measure has got very high input impedance. So, the current drawn by this will be almost 0, minimal. Yeah, so it will be some mega ohm or large resistance. So, I am not drawing any current from these P1, P2 terminals. Yes. So, that way the lead wire resistor effect is removed. This is a, what shall we say, a kind of a surface level explanation, because to inject a current like this and then measure like this, you will need, voltmeter. Instead of voltmeter, it may be an instrumentation amplifier.
Right, oscilloscope.
Yes. Or instrumentation amplifier, which gives very high input impedance and so on, and gives an output voltage corresponding to this amplified version. Current source also you need some electronic circuit to introduce this current. But once you have this, you can make it independent of the RL ones.
Lead wise resistance.
Yeah. I have one funny question. See, I have connected to P1 and P2. So sometimes students used to ask me, why not connect to this C1 and C2 itself? Correct. We are all same terminal.
Yeah.
Terminal is different, but it's
Yes. You measured the same thing. Well,
correct. Why not? So we will ask them to think about it.
I mean, you just move this. Yeah. Right.
Yeah.
Basically, that's what you're saying.
So one thing, maybe I can elaborate this C1 or maybe a better view. See, there is a contact there. So you have some wire coming like this, and then you are connecting this RTD wire there, and these are somehow connected.
Mhm.
So when you do this, definitely there will be some contact resistance. Let's say RC.
So you're adding another resistance
Yeah.
component.
Yeah. So suppose if I am measuring from this terminal, the voltage, then I will be measuring voltage across RX plus RC1.
Yes.
Similarly, at the bottom side, RC2.
Yes.
Yeah, not drawing properly, but I mean, I have this RX here, but RC1 and RC2 comes into picture.
You're introducing
Yes.
two more.
Yes. Now, we have introduced similar joints here, but there is no current through this, as you said. This current is 0, which is connected to the voltmeter. Yes. While here there is a fixed current. So, there is I into RC1 drop there, I into RC2 drop here. Right? Sometimes this, I mean, in the case of RTD, it may not be that significant, but in the case of a strain gauge, also this contact resistance can be noticeable, right? So that can introduce error. Right?
Even though the input impedance is high,
Yeah,
it still can.
Yeah. I mean, if what you meant is if I connect to this,
Yeah.
I'm not drawing any current this way,
Yeah.
but there is a voltage drop here at the junction that also I am measuring. So although the voltmeter measurement is correct, the drop here is getting added to the voltmeter. So once you use a 4 terminal, all these errors are gone. I mean, contact resistance error due to the contact resistance is removed.
So they are basically like two different measurements. You get
Yeah.
the current and then you get the voltage up. But if you try to do it in the same circuit, you're saying this contact resistance with the voltage drops and they will get added to
Yes.
the voltage.
Yes.
So and this is the reason why we
Yeah.
got
Yeah. So that's why we see 4 terminals. And this 4 terminal based measurement is there whenever you have precision measurement using some resistive element.
Now I'm curious.
Yeah. The
2.
2. So 2, obviously it cannot solve the entire problem. It will solve partially.
Okay.
This I will request the students to refer to some textbook.
All right.
Yeah.
But the 4 terminal is the most accurate.
Yeah.
And it makes sense.
Yeah. So this is the most used because it's relatively simple. In a bridge, this forms an additional leg or an additional terminal. It can solve large co-offset error due to the RL1 and RL2. But there will be some gain error due to that. Correct. We will give this as an assignment, and then maybe they should solve it by this because this is most used. And it's just a small extension of simple Wheatstone bridge. Yeah.
So in reality, are all 3 used?
All 3 are used. Suppose if you don't mind the error due to this contact resistance, and let's say it's a nearby the measurement unit and the sensing element, then that's fine. Then it's fine. So all these are relative.
Uh-huh. Because even the 3 pictures you showed, they were of different lengths, weren't they?
So I think
Or were they 3 different types?
I think that's for different applications probably. You mean this length?
Yeah.
Yeah, this is depending on the application. Maybe it's to measure temperature in a boiler or something. So, yeah. So we have got some idea about, how the temperature coefficient of resistance can be utilized to form a temperature sensor. Yes. And how good is this, as a straight line fit, or if you want better accuracy, what you need to do?
A polynomial fit.
Yes. And some sources of errors, the self-heating effect and the contact resistance issues. And then we have briefly mentioned about, I've drawn the NTC, the thermistor. Yes. It's thermistor which has negative temperature coefficient of resistance. As you can see, it has got very high sensitivity compared to the platinum-based temperature sensor.
And what are these different curves for?
I think they have provided for different type of
thermistors. What they're selling.
Yeah.
I see.
Yeah. Okay. Yeah. This is one of the pictures. So this is a thermistor and it's the wire. Right. So essentially, the range is not that great, but the sensitivity is very high. Right. So, and then you will have to use, here we have used a third order polynomial. Here you will have to use higher order, more complicated equations to represent it correctly. Right.
But the sensitivity is high.
Yes.
For smaller range.
Yes.
Compared to the
Yes. Yes. So that way, these are also widely used. So which is also a resistor, but resistance decreases with respect to temperature. Right.
As long as there's a change, right?
Yes. Yes. Yeah. So there are also some kind of thermistors with positive temperature coefficient of resistance, PTC, which again we will request the students to read a bit about it.
Okay, I imagine BW around.
Yeah. It goes, it increases, but not in a straight line. It's again in a different fashion.
Okay,
which is available in this reference. Just scan to just for what shall we say, the information purpose. Of course, we may not ask questions based on that, but that gives some kind of completeness for the thermistors. Just to mention, because it's not just NTC, there is also PTC, positive temperature coefficient of based, where thermistors with positive temperature coefficient of resistance. Correct. Because here NTC, we said it's due to the free electrons and holes that comes from the increase in temperature. But in the PTC, it will not be that.
It's a positive carriers.
Yeah, positive. So it is not due to the release of such electrons or holes. It is some other effector. Right? It is some what shall we say? Some agitation in the lattice of something. It's a different process that gives this feature. Right? But the curve I have seen for PTC, for example, one of the curves I've seen is it comes like this and then goes this way.
Oh, okay.
So
must be a totally different way.
Yeah. So it's not really used for sensing temperature, but if you want to use it as a threshold, as to detect temperature and then do some action, right? Then this kind of things are used.
Right.
While PTC, you can use it as a temperature sensor. You have a nice curve.
NTC.
Yeah, sorry, NTC. Yes.